All right, so let's continue with some more examples of related rates. All right, so for example, suppose that somebody in the train tells you that x and y are both differential functions. Of t, and that they are related by the following equation. Y equals x squared plus 3. Let's say that person in the train tells you to find dy dx when x equals 1, given that dx dt is equal to 2 when x equals 1. All right, this is a straightforward example, actually. Most of them do not come in this flavor, but it is good to practice these. First of all, we're given the equation y equals x squared plus 3. This equation is a quadratic, and it relates x with y. We are told that dx dt is equal to 2 when x equals 1, and we are finding dy dt. Okay, so the first step in almost any type of problem in this class, given that this is a calculus 1 class, will be to take the derivative. For this particular problem, we'll take the derivative implicitly with respect to t. So that means that when we take the derivative of y with respect to t, we get dy dt. And that is equal to 2x dx dt. And the derivative of 3 is 0, because remember, 0 is a constant. And the derivative of any constant is 0. Now, we have the values for x and for dx dt. We have them right up here. So we can simply plug in and we will get the result for dy dt. So 2 times 1 times 2 is equal to 4. So dy dt is equal to 4. Now, for this particular example, I gave us the actual equation that related both x and y. Now, that is almost never the case. Whenever you have a problem that involves related rates, this definitely will not be the case. So let's look at another example where this will become more clear. So let's say that a pebble is actually a very popular problem, or example I should say. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. Now, the radius r of the outer ripple is increasing at a constant rate of change of 1 foot per second. Now the question is, when the radius is 4 feet, at what rate is the total area of the disturbed water changing? So when the radius is 4 feet, at what rate is the total area A of the disturbed water changing? it is very useful to visualize this type of problems. If you ever open, you don't have to think about a pond. If you have a kitchen at home, which I hope you do, and you have a sink, fill up a cup of water with water. Fill up a cup of water with water, that's funny. Fill up a glass with water, and then let it sit until the water is completely calm under the faucet. And then let drops of water, single drops of water fall into the cup. And what you will have is, let's say if we have a top-down view, let's say this is the cup, the black circle. Then as the drops are falling, you have rings that get created of the ripple effect of the water as they move towards the edges of the cup. So that's what is happening in this problem. You have a pebble that you throw into a pond. If you throw it straight down, you will see those ripples of water moving in every single direction in the form of a circle. So for this particular problem, we're looking for area. So we should ask yourself, what are we looking for? What are we looking for? Because notice we didn't get any equations here. We just have information about what's happening. We have the rate of change of the outer radius is 1 foot per second, and the actual radius being 4 feet. But we don't have any information about what relates the radius to the area. Well, because we are working with circles, so notice that this is a circular motion. Because we're working with circles, we could relate the radius of these circles with the area of a circle, with the formula for the area of a circle. So if you again recall from 8th grade algebra class, the area of a circle is equal to pi r squared. So now we have an equation that relates radius to area. And it models what's happening here. If you pick any of these circles that get formed in the pond, all of them have a radius. And to find the area that they make at a particular point in time, then we simply do pi r squared once we have the radius for them. Like for example, if you are recording this with a camera in slow motion and you stop it, modern cameras can do this, and even in the past, this would be more difficult, but with modern cameras, you could stop time as you record from on top of the cup, and you could actually measure the diameter of the circles that get created. And as we know, the radius is half the diameter, so you get the radius from that. From that measurement, and then you can find the area for every single circle that gets created in that time loop. In any case, this being a calculus class, we will do a couple of things. We will take a derivative implicitly, but before we do that, I want to write down what our variables are. We know that r, we want to find out when the radius is 4 feet. And we know that the outer ripple is increasing at a constant rate of change of 1 foot per minute. So that's dr dt is changing at 1 foot per minute. Okay, so now we're pretty much set and ready to go, because we don't want to find the area. We just want to find the rate of change of the area when the radius is 4. So to do this, we will take the derivative implicitly on both sides with respect to t. The derivative of a with respect to t is simply dA dt. And that is equal to, well, pi is a constant, so we use the constant multiple rule with the power rule. So we bring down that 2, so we get 2 pi r times the r dt. So the derivative of r squared is 2r times pi, and because we took the derivative of r with respect to t, we have to multiply by dr dt. So you may see this mostly as 2 pi r. So you have 2 pi r dr dt. But we have values for r and dr dt, so we could substitute. So dr dt dA dt is equal to 2 pi times 4 times 1, which is simply equal to 2 times 4, which is 8 pi. So we have that when the radius is changing, well, when the radius is at 4 feet, the area is changing at a rate of 8 square feet per second. You should always put the units. Right now I'm avoiding the units here because I want us to focus simply on the derivations and whatnot. When you're doing these computations, you have to actually take into account that you are using these units. So I should have really written 4 feet times 1 feet per minute times 2 pi, but forgive me, I don't want to write all these things. So when you multiply feet times feet, you get feet squared. So you have 8 pi feet squared per minute. Okay, so I feel like I should have mentioned that because that's important. I mean, the units are very important when we talk about this related rates problem. I'm just skipping them from now. So what this means is that when the radius is 4 feet, the area is changing at a rate of 8 pi square feet per second. Per minute. Oh wait, no, I wrote per minute here. It's supposed to be per second. Yeah, per second. Should be seconds, so second per second. Per minute will be too long because these waves are moving very quickly through the water. So we actually have some guidelines for solving for related rate problems. So we actually have some few guidelines that will help us solve related rate problems. And I've been using them without mentioning them, but if you notice, before I began every problem, I identified all of the quantities that were given and the ones that we needed to find. So the first thing I should always do is identify all quantities given and quantities that we need to find. I always say, label each variable accordingly. This I always believe in, variable accordingly. So for example, if as soon as you hear somebody say, the rate of change of the area, you know that's going to be your dA dt. If you hear the rate of change of the radius, well, that's immediately dr dt. The rate of change of the speed, make the variable be s, so that will be ds dt if s is the speed variable. Every time that you hear rate of change, you should think of d dt with some variable here. Let's call it x. Okay, you always think of that. Okay, number 2, and probably the most important part of every single one of these problems is to write an equation that involves all the variables whose rate of change are either given or need to be found. So for example, again, if you're told to find the speed as related to the distance travel, then you should have a variable for speed and a variable for distance, especially if you're given the rate of change of those. The third step, probably the easiest step to be honest with you, because by now we have plenty of experience doing this, is to use the chain rule to implicitly differentiate both sides. Of your equation. This is probably the easiest step so far. And 4 is, after completing step 3, you want to substitute accordingly. And then solve for the required rate of change. Okay, so if you stick by these 4 steps, these problems don't become too difficult. The most difficult step is really writing that equation. That equation could be very complicated, especially depending on what's happening in your problem. This first problem with the pebble is very simple because we assumed that it was straight circles that were changing. But that need not be the case. I think I'm going to end this part here, and then when we come back in the next part, I'm going to do a few more examples involving related rates.